Okay, good afternoon again, everybody. Welcome. This is the third video lecture on induction. We've been talking about ordinary induction proofs so far. We've given some examples in previous videos. And there's actually all kinds of variations of the basic induction technique. There's things like strong induction and backwards induction and double induction. And we'll talk about some of those in due time. Today we're going to focus on one of the more straightforward variations of the basic induction, induction starting anywhere. That's what I call it. So we're going to have this template that looks very much like the one we had before for proving a universal statement for all integers in. All right, and before, this is the main difference. It was always positive integers. Now it's going to be just integers greater than or equal to b, where b, which stands for base, is some particular constant integer, maybe 0 or 4 or something. We don't always have to start at 1, is basically the main difference here. And we're going to be proving p of n for all n greater than or equal to b, p of n, all right? And there's an induction template that lets us do that. So we use induction on n, still say that. And I mean, the structure is still there. It's basically exactly the same. There was just one little difference in the base case. If we started at 1, as we've been doing, we prove p of 1. But now, if our smallest integer of interest is b, then we're going to prove p of b as the base case. Okay, that's the same b that shows up right here. My camera was pointed the wrong way last time, so I hope you can see all of this board. We'll find out after it's too late if you can't. Then we're going to have an induction step, which again is almost identical to what we did before. The one difference here is at the beginning, instead of fixing an arbitrary integer n greater than or equal to 1, like before, we're going to be fixing an arbitrary integer n greater than or equal to b, this base value. Okay? And then we're going to still do the induction hypothesis. Assume p of n for this constant value of n. You call it n naught if you really wanted to emphasize it was constant. And we're still going to prove p of n plus 1 to finish the induction step. And that is the template. All right. And we're going to do some examples now of this method. And before I get to that, let's just remember one of our recursive definitions from before with a slight modification. Products can also start, it doesn't always have to start at k equals 1. You could start it at k equals b and go k going from b to b of some term ak. That would be a sub b as the base case of the definition of products. And on the other hand, if you wanted product k going from b to m plus 1 of some ak, you could say recursively that's the product k going from b to n of ak, stopping at n, and then times the final term, which is a n plus 1. And that would be valid for every n, let's make sure, greater than or equal to b, so that would work there. And sometimes you make a convention about if the upper limit is less than the lower limit, it's 1 or something, but let's not worry about that. Product would be 1, sum would be 0 or something. Let's turn to the examples. Try to fit 3 of them into this video if I can. 3 more proofs. And for the first one, let's try to prove for all integers n at least 3, I'm going to claim that the product, k goes from 3 to n, of 1 minus 2 over k is 2 over n times n minus 1. And this is the part that I think got cut off in the last video. It looks like it's there, but again, no real way to tell until later. All right. All right. So this is a perfect example of something where, for instance, if you let k be 2 here, you'd have a 0 over there, and then the whole thing would be 0. So that's not what we want. So we actually really want to start at 3, not at 2 or 1 or 0 as our index there. All right. So b in this case, the base value is 3 instead of 1. And now we can start in with the proof. So we just follow the template religiously. Base case, and so what's the base case? We have to prove this. We're now n, so this whole thing, by the way, this whole formula is p of n. N appears here, here, here. Okay, so for the base case, we have to prove p of 3. And just to write out what that is, product k equals 3 to 3 of 1 minus 2 over k is equal to 2 over quantity 3 times 3 minus 1. And I'm not going to simplify anything at all, so just substituting n equals 3n, and the proof will do the simplifying. So let's do that. All right, so compute the left side. Product k goes from 3 to 3 of this term. So this whole thing here would be a sub k. You just plug in k equals 3. There's no multiplication actually happening here, with this in the base case. Just plug in 3. So we get 1 minus 2/3, which is 1/3. Okay. And all right, so another thing you can do on in these base cases, you can look at both sides separately. So then what's this side? 2 over 3 times 3 minus 1 is 2 over 3 times 2, which is 1/3. So the two sides agree. Or they're equal, or whatever. That's another way of presenting. Last time we were always doing chain proofs, but you can certainly just calculate the left side, stop, and then separately calculate the right side and see if you get the same thing. And we did, 1/3. So we did the base case. Let's move on to the induction step. All right, so we've got to fix the arbitrary integer. Again, here's the other place that changes just a little bit. Now it's an integer n greater than or equal to 3. Okay, and we get to assume p of n, this very statement right here. I'm going to write it again. Now it's an assumption. Assume for this fixed choice of n, this constant value of the parameter, that the product going from 3 to n, 1 minus 2 over k, is equal to 2 over n times n minus 1. All right, and then we have to prove this the next instance. So product k goes from 3 to n plus 1, 1 minus 2 over k. The k remains the same, but the n becomes n plus 1. Everywhere I see an n. Also on this right side. And again, I'm not simplifying, it's just replacing n's by n plus 1s everywhere. And the rest of the formula is also in there. Okay. All right, so how do we do that? Well, we're going to use a chain proof, a chain of equalities. We're going to go from here and in there. Let's see, so I guess I'm going to erase this now. I'm sure you've already memorized it. So for this proof, we can say we know, start off with a status word, we know. What do we know? So let's think about the left side. Product k goes from 3 to n plus 1, 1 minus 2 over k. And the only thing we know, really, at the beginning is the recursive definition of product. So this, by definition, is the product k goes from 3 to n of 1 minus 2 over k. all of that times the last term, the k equals n plus 1 term. So I put k equal n plus 1, multiplying that entire thing. And so that's by recursive definition of product. I hope I said product before. We were doing all these sums earlier. Okay, so we know that. And now, well, now magically this has appeared. The thing we assumed, this product going to n, is in the formula now. And so we already have assumptions about what that is. So we just plug that in. 2 over n times n minus 1. And then we also have this thing still there. And that's where we've used the induction hypothesis. So that's great. I just want to show and mention when you're using that. And we haven't gotten here yet, but of course we can now start doing some algebra on these fractions. Let's see here. Okay, so I can make this over a common denominator, right? m plus 1 over n plus 1 minus 2 over n plus 1. I'll try to show lots of steps here. Okay, and then now I can subtract. I get n plus 1 minus 2 in the numerator, so that's n minus 1 over n plus 1. And look, so these cancel, n is at least 3, right? So I'm not dividing, I don't have a 0 over 0 here. So I can cancel that. 2 over n times n plus 1. And, okay, and now to make it look exactly like this right-hand side, I'll go ahead and unsimplify the n back to being n plus 1 minus 1. And all of this was by algebra. Okay, so we did this, we succeeded, right? So we have this goal, and we got there by doing this chain of equalities. The end of that proof. Okay, so, I mean, these proofs aren't so bad, really. Once you've gotten used to the structure and, like, practiced, done, like, 10 of them and stuff, it's very repetitive, which is good, because you just get used to it. It's like tying your shoe or saying the alphabet after you've done the template enough times. I'm not saying, I mean, sometimes the induction step's going to be hard, but certainly in the ones we're going to do initially and I ask you to do, they won't be that bad if you've got all the recursive definitions under control. All right, so that's one example. Great, all right, so just perfect timing there. Let's move on to a different example that uses a different recursive definition from the beginning. And then I want to give you actually one of the laws of exponents. All right, so here's the statement. For every real x, for every m integer greater than or equal to 0, for every n integer greater than or equal to 0, I'm going to claim that x to the m plus n equals x to the m times x to the n. A law of exponents, as it's called, which you I'm sure have seen before, but of course for this proof we're not going to let ourselves use it as something we already know. We can only use the recursive definition of powers, not this fact, obviously. And let's just quickly recall before we get going, what was that recursive definition that I gave? X to the 0 was 1, and then x to the n plus 1 recursively was x to the n times 1 more x for every n at least 0. Now, you're probably aware that this works, at least for non-zero x, even if the exponents were negative integers or more general numbers, at least x was positive anyway, we are not going to try to prove that. We haven't actually defined or discussed negative exponents or fractional exponents yet. I'm not claiming this is the most general theorem that's true. There's more general versions of this, but this is the one we are able to prove now using the induction technique we've talked about. Induction so far for negative integers, if you're trying to prove something for all negative integers, Haven't really told you how to do that yet. That's like backwards induction or various other things. But let's not worry about that now. All right. For now, this will be enough. And there's actually a few other things going on as well, which is that you've got two variables, three actually. M and N are both integers. X is real. So to start the proof, we don't do induction right away. First, we have got to deal with this X here. So let's fix arbitrary real X, generic constant real number for this. And then when you get here, you actually have this sort of, maybe you have to do induction twice. There's something called double induction, where you have an induction inside another induction. That does happen, but it's not going to happen here. So here, we don't actually need induction for this guy. We'll just do what we've always done before. Fix an arbitrary integer, m greater than or equal to 0. Here, maybe I will actually call it m naught, just to really emphasize it's constant. Okay, I might regret that later, but I'm going to do that. And then we have to prove the thing inside. We still have one more quantifier. For all n integers greater than or equal to 0, x to the m naught plus n is equal to x to the m naught x to the n. This is our new goal. And this is the one where we're going to use induction on n. All right, so it's the inside statement. M is now a constant. N is still a variable at the moment. And I guess one of the reasons I put that subscript in is so you can see this entire thing here is the open sentence P of n. There's an n here. It has some other constants like x and m naught, but this is the P of n from the template. Okay, so it just has n as a variable. All right, so now let's do it. It starts at 0, by the way, not at 1, so induction starting anywhere is also being illustrated. So base case is, well, let's replace, we have to prove P of 0. In other words, we have to prove that x to the m naught plus 0 is equal to x to the m naught times x to the 0, replacing every n by 0. Okay, so there's a goal that we have to deal with. And, well, let's see. So let's do both sides. Let's calculate both sides separately. So we know that x to the m naught plus 0, that exponent is just a regular integer, by the way. So we certainly can use the fact that any integer plus 0 is 0, is itself. So m naught. So that's the left side. And on the other side, when I have to multiply by x to the 0, that's where I get to use the base case of this. So x to the 0 is defined to be 1. And then anything times 1 is itself. And of course we use, in addition to some algebra identities, I certainly use this definition right here. Okay. All right, and that's agreed. So the two sides are equal. Instantly, you didn't really need the naught. I mean, if you wanted the m, that's fine. Okay. But now that I've committed to it, I'm going to write m naught. Induction step. So starting at 0, so fixing the arbitrary n now, it has to start at 0. So it's greater than or equal to 0. Fix arbitrary integer. Yeah, the subscript would be too irritating, so I'll just call this one n. But it's important to realize it is, from now on, it's a constant, a particular choice of the integer n. Okay? And assume this statement here for that instance. Just copy it down. That's the induction hypothesis. And then we're going to have to prove the next one, where n gets replaced by n plus 1 everywhere. And we still have that m naught. That's just part of the expression. That doesn't change. Right? Okay, so let's try chain proof here. Never have good board space here, but that's the way it is. So we know, to start the chain, let's go with the left side here, x to the m naught plus m plus 1. Okay, what do we know about that? Because I'd kind of like to use this, which is true for every n, this recursive definition. And there's one thing I have to do first, though. I really need to move those parentheses over inside the exponent. So it looks exactly like this, with plus 1 on the outside. That's associativity of addition as a reason why I can do that. Okay? And now that I've done this, keeping in mind this thing's true every n. In this case, so the n here is going to be this expression, m naught plus n. I can use it with that choice of the n here, because it's all n. All right? So that's where that recursive definition is going to get used. And it's going to be x to the m naught plus n times one more copy of x. And that's by recursive definition of exponents. All right. So now we can use this. So the assumption tells us about this expression that showed up right here. It says that x to the m naught plus n is x to the m naught times x to the n. And we still have this extra x. All right. And then what? So we're trying to get here, having x to the m naught now. Once again, I want to kind of reassociate the parentheses, this time using associativity of multiplication. So move that over. Real multiplication is associative. We did have an axiom about that. And now, x to the n times x, by using the recursive definition backwards, this time for this value of n, I can change this back into that. Again, that's by the recursive definition of powers. And the reason I wanted to do that, of course, is because that gets me to the right side of the goal. I started with the left side, I did known steps with reasons, and I got to the right side. So that completes the induction steps and this proof. There you go. All right. So let's do one more example. There'll be other laws of exponents in various homeworks and stuff that you can try to prove by similar techniques. Oh, but one thing, notice how we fixed the m. That can be useful when you have two parameters. You don't necessarily have to do induction nested inside itself, although that does sometimes occur. But what I just showed you is also a common situation. All right, so let's see. Let's prove, without using differential, let's prove for every integer n at least 4, 2 to the n is strictly greater than 3 times n. All right, inequality. Starting at 4. Okay. And if you're wondering why I started at 4, well, as a remark, if you let n equals 3, first of all, let's label it. So this is p of n, 2 to the n greater than 3n. That's a statement involving n, open sentence. What's p of 3? Just as an example before the proof. P of 3 says that 2 cubed is greater than 3 times 3. In other words, it's saying that 8 is greater than 9, which is false. So, well, that's why we start at 4. Okay, so you can't always start at 1. It might not be true. But the hope is that from 4 onward, it will be true. Let's try to prove it. So base case, we use induction on n. We should say that. then maybe people would figure it out. We can start going into the base case, but you should always label stuff. Okay, base case, prove P of 4. So in other words, you have to prove that 2 to the 4 is greater than 3 times 4. All right, and okay, so you can use the definition a bunch of times. I won't belabor that. I'll just say we know, 2 to the 4 expands into 2 times 2 times 2 times 2 by that definition, which is 16. 3 times 4 is 12. And of course, 16 is greater than 12. So that is true. Base case is true. On we go then to the induction step. So we follow the template. We fix an arbitrary integer n greater than or equal to 4, whatever the base value is, in this case 4. We assume that 2 to the n is greater than 3n. And we have to prove that 2 to the n plus 1 is greater than 3 times the quantity n plus 1. There is the setup for the proof. All right, now we've been doing a lot of equations before, equalities. Here's an inequality. You remember that greater than is a transitive relation, so I can do a chain proof here. A chain of inequalities. That's permissible. If I can find a chain of greater than relationships that I know that start here and in there, well then I've proved this. So that's what I intend to do. We know, and let's take a look. So what do we know about 2 to the n plus 1, which is the left side of the goal? I don't know this, so I'm not going to write that. But what I do know is the recursive definition of exponents. It's actually equal, and you're allowed to have equals mixed in, by the way. That's allowed. 2 to the n times 2 by recursive definition of powers. All right, so that's gotten us going. But look, so now I have an assumption about 2 to the n, that 2 to the n is greater than 3n. Okay, so this quantity here, that's still true if you multiply both sides by 2, because 2 is positive. So this is greater than 3n times 2 by the induction hypothesis. Just because I have my reasons here, this refers to the previous thing. So this is greater than that, is what I mean here. So then I can put a reason over here. And now, all right, so we have to be a little bit careful. What am I trying to get? I'm trying to get 3n times quantity n plus 1, which is like 3n plus 3. And here I have something slightly different than that. I have 3n times 2, and this is what makes this proof a little bit tricky. I'm going to do something that might seem a little bit funny. I want to think of this, of course it's equal to 6n, but I want to think of it as being 3n plus 3n for a second. Why? Because over here, upon expansion, we're secretly going to be trying to get to 3n plus 3. So I want to see a 3n there. Okay. And there it is. But then I actually have something here that it's more than what I want. 3n, I want to just have a 3. Okay. The thing, though, is what's n here? N is greater than or equal to 4. Okay. And just as a little sidelight, since n is at least 4, 3n is at least 12. And so this is getting used. So I can take this second copy of 3n and say, well, that's greater than or equal to 12. And which is, by the way, which is strictly greater, let's do it slowly, greater than or equal to 3n plus 12. That's only true because n is at least 4. Okay. But that's more than what I need because I really wanted a plus 3, and 12 is greater than 3. So 3n plus 12 is strictly greater than 3n plus 3. And then 3n plus 3 is equal to 3 times quantity n plus 1. All right, so we have to be a little bit careful here. So what's actually happened in this chain is I've written down a bunch of real numbers, and I've said that A is equal to B is greater than C is equal to D, greater than or equal to E, greater than F, equal to G, where this is A, B, C, D, E, F, G. So I have a whole bunch of stuff here, but the point is, and as you can check, because everything is either an equal or a greater than or equal, and at least one of them was a strict greater than, then it's, by looking at this expression and using transitivity of the different relations over and over again, this does give us A strictly greater than G. In other words, 2 to the n plus 1 strictly greater than 3 to the n plus 3 times n plus 1 as needed. So I don't know if that ever happened before. It doesn't always have to be strict greater every single time, right? You can have some of these being greater than or equal to and so on. You do need at least one strict greater when we have it. We have it here, we have it there. All right, and now we've reached the goal. So there's the end of that proof. And that's probably a great place to stop. There's some other examples in the section, but I'll let you go and read the book for that. See you next time.